Alright guys, in this video we'd like to plot a cardioid in the polar plane. So remember that the equation of the cardioid that we want to plot here is r of theta is equal to 1 minus sine of theta. And so the idea here is that as theta changes, as theta goes around the circle, so we're going to go from 0 to 2 pi here, but as theta goes around from 0 to 2 pi, the radius is going to change corresponding, and we want to plot the points r comma theta for each of these values of theta. And so let's make a little table. So theta is the independent variable here, so we're going to pick some values of theta, and then plug in our values of r, and let's just see what happens. So let's start with theta equals 0. Remember, theta equals 0 is just the, I'll sketch it over here, it's just this ray which emanates from the pole. Remember, the origin is called the pole in polar coordinates, in the direction of what's usually the positive x-axis. And so we plug this in for theta, and our radius then becomes 1 minus sine of that angle, so 1 minus sine of 0. And that's, of course, sine of 0 is 0, so this is just 1. And so the point on the polar plane here that corresponds to this value of theta, theta equals 0, has a radius of 1. So we go out in the direction of theta equals 0, we go out to a radius of 1. Okay, and we're going to continue this for a few points along, a few values of theta along this polar axis, and then see if we can understand what's going on here. So now we plug in theta equals pi over 6. The radius is then 1 minus sine of pi over 6. Sine of pi over 6 is, of course, 1/2, so this is 1 minus a half, or just a half. All right? So as we go out the ray in the direction of pi over 6, this time we're only supposed to go out to a length of 1/2. All right? And then we continue this. We just go around and around. So when we plug in pi over 4, our radius is now 1 minus sine of pi over 4, so 1 minus root 2 over 2. This is smaller than a half because root 2 over 2 is larger than 1/2. So 1 minus that is going to be smaller. And we don't need to get it exactly where it's supposed to be, but let's say it's about here. And again, we continue on. We don't have to write down every single value in this table, but we'll do the first quadrant. So pi over 3. This radius is going to be 1 minus root 3 over 2. Again, it's getting smaller. So in the direction of pi over 3, this direction, our radius is now 1 minus root 3 over 2. Okay. And then finally for the first quadrant we get to pi over 2. And sine of pi over 2 is, of course, 1. So the radius at this point is 0. So that tells us that when if we want to go in the direction of the ray, pi over 2, theta equals pi over 2, but we're supposed to go 0 units out. So that tells us actually we stay right at the pole. All right, so this point that corresponds to the angle of pi over 2, that's just a point at the pole. Okay, and so as we go through here, these points we just connect the dots just like we normally would, but we do it in the polar plane, and so we get this portion of the curve right here. Now I'm not going to plug in the rest of these, you should do it for yourself, but as the way that sine works, sine is an even function, so the values of sine in the third quadrant over here are the same as the ones over here. So this is just going to be a reflection over what we would normally think of as the y-axis. And so in this direction, pi, that value is just 1. This one's 1/2. Whoops, that's not where 1/2 goes, though. This is 1/2. And then it counts in from there, just like we did before. Okay, and so this should be a mirror image on this side. And so there's the top half of our cardioid. Now as we move down into the third and the fourth quadrant, things start to change because now sine becomes negative down here. So when sine becomes negative, let's plot a couple values of this. Let's throw in 7 pi over 6. For angle 7 pi over 6, now we're doing 1 minus sine of 7 pi over 6. And we said, of course, that sine of pi over 6 is 1/2, but sine of 7 pi over 6 is negative 1/2. So this becomes 1 plus a half, or 3/2. So now the curve is getting further away from the pole. So this is 3/2. 3/2, of course, is this circle. We go all the way around to this angle. All right. as we go around, so this is going to be getting wider here, fatter a little bit. And as we get down to 3 pi over 2, so it's going to keep building up and getting longer and longer, the radii, instead of shorter and shorter. And so at this point, 1 minus sine of 3 pi over 2, this is 1 minus a negative 1. So 1 plus 1, which is 2. And so this is the point down here where this curve is going to cross, and it's going to do so in somehow like this. It just keeps getting longer and longer and longer, the radius, and then obviously it's got to close out on this side. Alright, so this thing should be totally symmetric. It's a little choppy the way I've drawn it. I've plotted it point by point up to a point. Once we notice the pattern, we can kind of fill it in. But this shape right here is called a cardioid, and there are lots of different ways to represent cardioids that are all similar to an equation like this. But this is the one that kind of has the shape of a heart, so that's why it's called a cardioid. It looks a little bit like a heart.